All right, today we're diving into something truly mind-bending, conformal field theory. This is all about one of the most elegant ideas in physics, the idea that symmetry isn't just pretty, it might actually be writing the fundamental laws of our universe from the ground up.
So, get this. What if we could figure out the laws of physics, not by smashing particles together in giant colliders, but just by demanding that the rules be perfectly, logically consistent? I mean, seriously, what if the universe could be solved like a puzzle just by using pure thought? That's the absolutely wild idea we're digging into today.
And the whole thing kicks off with this really profound idea. The most fundamental theories, the ones that get down to the real nitty-gritty of reality, are also the most symmetric. It's like the deeper you dig, the more elegant and balanced everything becomes. The ultimate theory? It would have to have the most symmetry possible.
And that brings us to the hero of our story, conformal symmetry. So what is it? It's the symmetry of a system that looks the same no matter the scale. Think about it. It's physics where size just doesn't matter. You could zoom in forever or zoom out to infinity, and the laws of physics would look exactly the same. It is the absolute peak of simplicity.
Okay, so if you have a theory that's this symmetric, how do you even work with it? You're going to need a rule book, right? A special mathematical language that can actually describe this wild, scale-free world. Well, that language has a name, the Virasoro algebra. And honestly, the best way to think about it is as the grammar for any two-dimensional conformal field theory. It's not just a few rules. It's this incredibly powerful, infinite set of rules that defines every possible interaction, every particle, every force, everything that can happen in that universe. Now take a look at this. This equation is really the heart of the whole thing. These L operators you see, they're like the verbs of this grammar. They're the actions, the things you can do in the theory. But the really cool part is that little letter C. That's the central charge. Think of it like a unique ID number, a serial number, for each and every possible conformal field theory. If you change C, you're literally talking about a different universe with a whole new set of rules. So how do you use this grammar to actually build something? Well, it's a bit like building a family tree. You start with one fundamental thing, what we call a primary state, that's your basic building block. Then you just start applying those V operators, the verbs from the Virasoro algebra, over and over again. And just like that, you generate this entire conformal family of all related states and particles. It all grows from a single seed. Okay, but here's the catch. Just because we can write down a theory on paper doesn't mean it actually describes reality, right? So now comes the tough part. We have to figure out how to sift through all the mathematical possibilities and find the ones that could actually be real. And the very first, most important filter we have is a concept called unitarity. It sounds complicated, but the core idea is super simple. Probabilities have to be positive. You just can't have a negative 50% chance of something happening. It makes no sense. So any theory that spits out negative probabilities, it gets thrown right in the bin. It's not physical. And this is where you start to see the sheer scale of the problem. Mathematically, the Virasoro algebra lets you cook up an infinite number of these theories, an infinite number of choices for that central charge C. But the vast, vast majority of them are, well, they're junk. They're not unitary. Only a tiny, rare handful could possibly describe a piece of our universe. So how in the world do we find those needles in an infinite haystack? We use this amazing mathematical tool called the kite determinant. You can think of it like a detector that's specifically designed to hunt for something called null states. These are weird states that have a size, or norm, of 0. Now in physics, anything real has to have a positive size. So finding these zero norma states is like finding a flashing red light. It tells us we're right on the boundary of what's physically allowed, and it points us directly toward those special unitary theories we're looking for. And here's where the magic happens. When you actually solve the math and find out where this Kite determinant hits 0, you find something incredible. It turns out that only very specific, discrete values for the central charge C and the energy H are allowed. It's not a smooth, continuous range of possibilities. It's a quantized list. It's like we've discovered a periodic table for all the possible, well-behaved conformal field theories out there. So that's one way to do it. Start with everything and filter it down. But there's a completely different approach, another way to attack the problem that's just as powerful. Instead of filtering, this method builds a theory from the ground up, based on one simple, beautiful demand: perfect self-consistency. Yeah, there's another way to solve the whole puzzle, and it's all about demanding perfect self-consistency.
The idea is that a true law of physics can't contradict itself. The answer you get shouldn't depend on how you calculated it. This whole approach is called the conformal bootstrap. And the best way to get your head around it is to think about solving a Sudoku puzzle, right? When you start a Sudoku, you don't know the final answer. All you have is a set of rules. Each number can only show up once per row, column, and box. But just by enforcing those consistency rules over and over, you're backed into a corner. There's only one unique solution that can possibly work. The bootstrap is basically Sudoku for physics. And this is the core of it, right here. You can calculate what happens when four particles interact by grouping them in different ways. You could combine the first two and the last two, or you could combine the middle two first. The bootstrap principle is just the ridiculously strict demand that no matter which way you calculate it, you must get the exact same answer. It sounds simple, but that one constraint is so incredibly powerful it can be enough to solve the entire theory, no other input needed. All right, so we've got these two incredibly powerful methods. One filters out the unphysical theories, the other demands perfect consistency. We've massively narrowed down the possibilities. So, what's the payoff? What do the theories that actually survive this brutal gauntlet look like? After all that hard work, all that math, what are these special, unitary, self-consistent theories that made it through the filter? What do they actually describe? Well, they're called minimal models. And they are just beautiful. They're the simplest possible conformal field theories you can have. They only contain a finite number of fundamental particles, or primary fields, and they line up perfectly with that special, discrete list of theories we found earlier, the ones with a central charge less than 1. You can really think of them as nature's most basic, elegant building blocks. And I want to be clear, this is not just some abstract mathematical game. These minimal models show up in the real world. They perfectly describe what happens to real physical systems right at a critical point. We're talking about a magnet at the exact temperature it stops being magnetic, or a pot of water at the very instant it starts to boil. In those moments, the system loses its sense of scale. It becomes conformal, and these theories give us the perfect language to understand exactly what's going on. So if minimal models are like the fundamental atoms of this conformal universe, what's next? Physics is obviously more complicated than that. So how do we use these simple, elegant pieces to build more complex, richer worlds? Well, you start adding more tools to your toolkit. You can use something called current algebras to add whole new types of symmetries into the mix. There are clever tricks like coset models that let you construct brand new theories from the ones you already understand. And then you have things like the West-Zumino-Novikov-Witten models, which are absolutely essential building blocks for things like string theory. Each of these is a way of building up from the simple to the complex. And it all circles back to this one central theme, which is captured perfectly here. We have found a whole class of theories where the symmetries aren't just a feature, they determine the entire theory, completely and uniquely. You don't have to guess the laws, you just have to find the symmetry and the laws follow. And that leaves us with a pretty incredible thought to end on, doesn't it? As we stare at the biggest mysteries out there, dark matter, quantum gravity, you name it, maybe the answer isn't just waiting for a bigger, more powerful experiment. Maybe the solution is already out there, hidden in plain sight, just waiting for us to discover the right, beautiful symmetry that writes the next chapter of physics.